If you remember from before, if we have a beam or a bar, let's see. We put it in axial loading. We know we can find the plane stress is defined as the axial force divided by the area that's perpendicular to the x-axis. We also know from Hooke's law that plane stress is equal to E, which is the modulus of elasticity, or Young's modulus. So this is plane stress. This is plane strain. We also know that we can find plane strain as deformation in the x direction divided by the original length in the x direction of that member. So when we put this member, in this case in tension, if we look at the cross section, so if I turn this and put it this way, but this is the cross section. When I load it in tension, we know that this cross section decreases in size. In order to account for the total volume, we know that this length increases a little bit, because the length times the width times the depth, which is the volume, remains constant. So in this case, if we put this in tension, these two dimensions shrink. Therefore, this dimension has to elongate because the volume is constant. When you put this in tension, again, we can find the stress involved by looking at the area divided into the force that's applied. We can apply Hooke's law to find out what the strain is. We can use that to find out what the elongation is, in this case, to see how long that's, or how much that's changed. We can also look at what is going on with this, which is axial strain. Because this is shrinking in that dimension, this causes a strain in both the y and the z directions.
Excuse me, what is that number for E of the x on top?
Right here?
No, down one.
Here? Axial strain, which is epsilon sub x. This is the definition of axial strain. You can go back and define it this way. So you could say this is this divided by that, or you can define it this way. Usually it starts off from Hooke's law, but you can also relate it to other information of interest, such as elongation.
I was saying, what is that a number? Is that 2 times 12?
I haven't put any numbers in this yet.
Oh, what is that? Is that EX? I don't know what that says after
Here,
on the bottom. I don't know what it says after.
I said, all I'm saying is, when you have an axial strain in the x direction, because you're shrinking the sides in the y and z direction, it creates an axial strain in each of those dimensions as well. So when you put this in tension, you create an axial strain caused by that force. The fact that the cross-section shrinks tells you that it also causes a strain in both the y dimension and the z dimension. If you look at how we can relate these, we have nu, which is not a neutrino in this case, different field. And it's looking at the ratio of strain in either the y direction compared to the x direction, or it's also equal to the strain in the z direction compared to the x direction. This value is called Poisson's ratio. It is a physical property of the material. And specifically, it is equal to E divided by 2G minus 1. And again, this is a definition of Poisson's ratio, where E is the modulus of elasticity which is one of the values given on the table that I sent to you earlier. So this is the modulus of elasticity. G is the modulus of rigidity. And again, both of these are physical properties associated with any particular material. It is, since it's a physical property, it is tabularized. You can use this to calculate Poisson's ratio, which in itself is a physical property of the material. Now, why would you want to know something like that? A couple of other things about Poisson's ratio. Okay. It is always a positive value. If we go back and look what is happening, we know that one-dimensionally, but if we look at multi-dimensional, we can come up with an expression such that the strain in any one dimension is looking at a contribution caused by any of the three axes. So in the x direction, it's going to be sigma x over E. Then if you use Poisson's ratio, it's going to be so if you have a material that, let's say, you only load in one direction, if it is only loaded in this one direction and you have no forces in the y or z direction, then it is one-dimensional. So if there's no forces in the y direction, we have no stresses, plane stresses created in the y. If we have no z forces, we have no plane stress in that direction. So this evolves down to, this is going to be 0, this is going to be 0. So we have this, which is our basic old Hooke's law for one-dimensional loading. But we can also find out what's going on as far as strains actually in the other directions. We still have none of this and none of this, but we will have a strain in the y direction that's caused by the force in the x direction. And that's because that cross-section is shrinking. Likewise, if we look at what's going on in the z direction for strain, there is again none of that because there are no forces in that direction. But we can again find actual strain in that direction. And how might that be beneficial? If you go back, remember that this is a definition of plane strain. So if we cross multiply here, deformation in the x direction is equal to the original length times whatever strain we've created. We can find out the dimension. And we know that the final length of the member is equal to the original length of the member plus or minus deformation in whatever dimension we're looking at. And again, if we have this thing in tension, this is going to be plus. If we have it in compression, that's going to end up being minus. So just like you did for extra credit on your exam, we could find out how much that bar has elongated by looking at what's going on from the stresses that we've calculated and knowing the original lengths. If, however, we have a three-dimensional object, okay, and we look at the forces involved, so for example, if this is X, this is Y, and this is the Z dimension, if we have a force applied in this manner on its face, we can find out what that force is by looking at the area that's perpendicular to it. If we find out what this value is, we can substitute it back into our equation, find out what the strain is in any particular direction, and then we can ultimately look at it if it's three-dimensional as to what the final length might be. We could also calculate the plane strain, the plane stresses in any of the axes to see if it is safe. I'm not sure. So let me give you an example of this. Okay. Let's say I gave you a bar that had certain dimensions. So length in the x direction is 8 centimeters. Length in the y direction is 4 centimeters. If we turn it around, the depth is 3 centimeters. And then I gave you forces that were acting in a particular direction. Like if this is the x direction, let's say this is force in the x direction. I could look at the force divided by the cross-sectional area that it's acting on, and I could come up with the plane stress that's in that direction. If I gave you a force in the y direction, I could calculate the plane stress there. Likewise for z. So if I gave you some kind of three-dimensional material, I gave you the lengths involved, I gave you the forces involved, you could calculate each of the independent plane stresses involved, and by looking at these values compared to sigma yield for whatever that material might be, you could determine if the material is safe. If I go back and look at these values that I've calculated, and I plug them, for example, if I look at this, and I go back and plug this in anywhere I see a sigma x, anywhere I see a sigma y, I go back in and substitute that. And then likewise, anything I see as sigma z, I come back and substitute that in here. And I can calculate Poisson's ratio so I just wrote that backwards. Excuse me. And wherever I see this, I'm going to substitute that in here. And again, E is Young's modulus, which is the physical property of the material, which you'd find from your table, or I would have given it to you. You can calculate the strains, both axial and lateral, in each direction. And again, you know that the final length in any one dimension, if I use x, is equal to the original length in x, plus or minus that deformation. And we know that the deformation is equal to strain times the original length. So we have a way, if we load up anything three-dimensionally, we can determine the plane stresses to see if it is safe, comparing it to the yield value. We can calculate Poisson's ratio, looking at the physical property of Young's modulus, plug this into our plane strain equations, come up with these values, and then come up with a final value of length to see what happens. So is this safe? And then what is the final dimensions of this, knowing that the volume has to be the same. If you have, I'm not sure what your higher math capabilities are, but if you look at this, has anybody ever worked with determinants in any of your math before? And if you do determinants, you take the coefficients, if you take the coefficients out of an equation, you can put it in a determinant. This is a 2 by 2. You cross multiply, so this would be 2 times minus 6 minus 1 times 3. So this is minus 12 plus 3. That value would be 9. You can solve this set of 3 simultaneous equations very easily using determinants. Has anybody had those in any of your math so far? If not, this is sort of a plug and chug type thing. But this is the last thing I want to cover on plane stress, plane strain. Again, I did not include this on the exam you just had, but there will be a little bit of this on the next exam. And I do have a quiz for you to take home tonight and do back on Wednesday that's very simplistic. Any questions on this? Okay. If not, then I would like to send you that quiz and go over it with you very quickly.
Professor, is there any way that you can go over an example with this method using like actual numbers?
Okay, let me okay. Okay. Okay, let's say we have a bar that is 12 centimeters long. It has a height of 4 centimeters. If we turn this sideways, four centimeters, and let's make this one dimension 2 centimeters. So this is a cross section. Let's say we use our friend aluminum 1100. And let's say I load this such that we have a force in the x direction. Which would be going like that of 800 newtons. Let's see, we have a force going in the y direction of minus 500 newtons. So in this particular case, and let's say we had a force in the z direction of 1200 newtons. And again, that would be coming out of the board. Since it's positive, it would be coming out of the board in this direction on this side, going back into the direction on that side. Okay. So I might ask you, what about safety for our system? And then what are the final dimensions? Okay. Again, we've made this aluminum 1100. The first thing I would do is go in and list my physical properties so I know what I'm working with. So for aluminum 1100, I know that my yield value for plane stress is 95 megapascals. I know my shear stress is 55 megapascals. I know my modulus of elasticity, which is again a physical property, is 70 megapascals. And I know my modulus of rigidity, which is again a physical property, is 26 gigapascals. Okay. And again, I've gotten these values from either the textbook or the chart that I've given you, or I might give them to you if I want you to use something different. Okay. This thing is automatically in equilibrium because I've given you the forces in the x, y, and the z direction. So when I look at safety, in this type of thing, we only look at plane stress. So I look at plane stress in the x direction, where this is the x direction. We know that is the force in the x direction divided by the area that is perpendicular to it. What is the force in the x direction? It is plus 800 newtons. And what is the area? If I turn this sideways, this force is acting on this face. So that is 4 centimeters, which is 4 times 10 to the minus 2 meters. 2 centimeters, 2 times 10 to the minus 2 meters. Okay. So since I'm doing this, I'm going to trust somebody to do their calculators with me. So we're coming up with the same values. Okay, what did you get for this?
Is it just 1 megapascal?
Can everybody see and hear me again? My end just cut out. So everybody with me so far?
Yes.
Okay.
Yeah,
What did you get for a calculation?
1
1 megapascal.
1 megapascal. Okay. So is our system safe from the X stress? The answer is yes. And again, you're going back comparing that to the yield value. So 1 is much less than 95. If I go back and look at the Y value, we know that's the force in the Y direction divided by the area is perpendicular to that. What is that force? It is minus 500, so that side is in compression. And what is the area it's working on? It's working on this side, which is a 12. So if I take this like this, and this is acting down like this, I know that this side is 12. And when I come down, I'm looking at this side that's going in, which is going to be 2. It's going to be 12 times 10 to the minus 2 meters, and 2 times 10 to the minus 2 meters. So I know that this is going to be a compressive plane stress. Somebody let me know what that value is.
Negative 0.21 pascals.
Okay, what'd you get? Negative
0.21.
0.21 megapascals. Okay. So again, we need to compare this back to the yield value, which is 95, much less. Does it make any difference if this is plus or minus? No.
it's not.
For safety, because we know that when we went back and looked at how it performed, attention, this is the yield value. This was the ultimate value, and as long as you were operating along this dimension, you're okay. And this is for positive forces. It has a mirror image on this side. So if it's compressive, It looks exactly like it does for positive as long as you're working with metals. So this is safe, this is safe. We still have to look at the last one, which is the plane stress in the z direction. That's going to be the force in the z direction divided by the area that's perpendicular to it. That force is 1,200 newtons. And we're looking for the area that's perpendicular to this. Remember, this z force is acting out of the board here, behind the board, because it's in tension. So the area it's acting across is a 12 now times 4. And what do we get for that value?
I got 0.25 megapascals.
Okay. Again, this is positive. We're comparing this number to the yield value, so again, it is very, very safe. Any questions on how we determine the plane stress in each direction, and then how we determine whether it was safe or not? So what I'm going to do is I'm going to save these values.
I have a question.
Okay.
Okay, so for the value that we just got for Z, we're comparing that to the yield for Y.
Okay. If you remember, for any material, it has a yield value and an ultimate value for plane stress and also for shear stress.
Yep.
So this yield value is fixed. No matter what axis you're looking at, depending upon what the material is. So whenever you calculate the plane stress in the X direction, Y direction, and Z direction, you calculate these values, and then for safety, you always go back and compare it to the yield value. Does that answer your question, Heather?
Yeah, yes. It's Monday.
Okay. So I want to save this. I'm going to put these values right up here. So sigma X was plus 1 megapascal. Sigma Y was minus 0.21 megapascals. And sigma Z was plus 0.25 megapascals. Okay? And again, these are the plane stresses we calculated in each direction. For our aluminum 1100, we compared it to the yield strength. Everything was safe. And again, when we do these, we're only worried about plane stresses. We're not worried about shear stresses. Okay. Any questions on what we've done thus far? And the next thing I want to do is calculate my Poisson's ratio. Before I forget it, when we talk about Poisson's ratio, anybody take any French? Do you know what Poisson stands for? What it translates to? You might see this on a menu somewhere.
It's fish, if I'm not mistaken.
That's right, sir. Poisson is fish, so this is Mr. Fisher's ratio. So this is E divided by 2G minus 1. So for aluminum 1100, our E value was 70. Our G value was 26. So that value comes out to be at 0.346. Anybody else get that? Hopefully everybody else got that.
Yes, that's what I got.
What are the units for Poisson's ratio? It is dimensionless, because this is going to be gigapascals divided by gigapascals, which cancels out, -1, so it's going to be dimensionless. Remember, this always has to be positive. So if you ever get a negative number there, you know you've done something wrong. So again, I'm going to put that little tidbit of information over here. So Poisson's ratio for aluminum 1100 is equal to 0.346. If this textbook was really good, in addition to giving you these yield values, modular elasticity, they should have also given you Poisson's ratio for that material, because that's a physical property, it's constant. Okay. Now we have everything we need to go into that three-dimensional equation. Excuse me. We know that plane stress in the x direction is going to be in fact impacted by the forces and the stresses that they create in each of the three dimensions. So this is okay. So what we're going to do now is everywhere we see an E, we're going to go in and substitute this value, because this is the modulus of elasticity for aluminum 1100. I've just converted to 1 Pascal, and then we know a Pascal is a Newton per square meter. This is going to get busy, so I won't do it for all of them, but I'm going to substitute it here, 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 and here. Okay?
Excuse me, what does that say? He says 7 times 10 to the what?
Where are you at? Here?
70 times 10 to
70 times 10 to the 9th, because that's what a giga is, 10 to the 9th, Pascal. Pascal is a Newton per meter squared. If you feel better putting in 70 gigapascals, you can do that, but then you have to convert this into units that are going to cancel out, like units. So I've gone ahead and done that for you. Okay. Next, we're going to go and wherever we see Poisson's ratio, and I'm not going to do it in all of them, but I'm going to do it in just the top one. Wherever we see Poisson's ratio, we've already calculated what that is. So this is 0.346, 0.346, 0.346, 0.34. Wherever we have a Poisson's ratio, we substitute that in. Then finally, we look at the stresses that we've calculated earlier. Wherever we see a sigma x, we substitute in the value that we calculated for sigma x, which was plus 1 megapascal. 1 megapascal is 10 to the 6th Newton per meter squared. Again, this is 1 megapascal. Wherever I see this, I'm going to substitute in that value, and I've circled that with a red.
Can we do them right now, just so we can make sure we did the calculations right?
Say that again.
I said, can we insert them all now and see if we did it right?
Now, do you want to put them all in now? Okay.
Yeah, at least the first one.
Tell you what, I'll just do it on this top line. How's that?
Yeah, that's fine.
Okay. So the next thing I'm going to do is wherever I have a sigma y, we've calculated what that value is for plane stress in the y direction. I'm going to put that in. In this case, this is minus 0.21 megapascals, and we know megapascal is 10 to the 6th newtons per meter squared. So wherever I see a sigma y, I'm going to substitute in this value. And then finally, wherever I have a sigma z, I know we've calculated that value, so I'm going to put that in for wherever I see that. So in that case, this is going to be 0.25 megapascals, which we know is 10 to the 6th newtons per meter squared. Okay. So I'm going to go back. Right now, just for ease of space, I'm going to erase the calculations for strain in the y direction, strain in the z direction, and we're just going to calculate it for x. Everybody with me? So I'm going to expand this, so hopefully it'll be a little bit clearer. So sigma x is going to be the contribution we have for the x direction. So sigma x was 1 times 10 to the 6th newtons meter squared divided by E, which is 70 times 10 to the 9th newtons per meter squared, minus Poisson's ratio, which is 0.346, times the plane stress in the y direction we calculated, which was minus 0.21 times 10 to the 6th newtons per meter squared, divided by E, which was 70 times 10 to the 9th newtons per meter squared, plus Poisson's ratio again, which is 0.346, times the z value, which was 0.25 times 10 to the 6th newtons per meter squared, divided by 70 times 10 to the 9th meters squared. Okay?
Why would it be a negative?
So, say that again?
Why are we adding the
Oh,
last
that's
part?
right. Thank you. Should have followed my sign. That is a minus. Thank you. So, like units, like units, like units, like units, like units, like units. So our final answer is going to be what? It's going to be dimensionless, and that's what you expect plane strain to be. So, for those of you hopefully working your calculators, let me know what this value comes out to be.
I got an answer.
Okay, what did you get?
Okay, that's 1, 2, 3, 4, 5. So that's 1.4 times 5 to the negative 5.
1.4 times what? 10 to the minus 5?
Yeah, 10 to the minus 5. I think.
Okay. Anybody else get that number? Or something close to it?
I got something close to it. I got 1.201 times 10 to the negative 5.
Okay. Anybody else get anything? Thank you, Tom. That's all right. Okay. Somebody else got 1.4. Okay. Just for argument's sake right now, let's go with the 1.4. Okay. So you've done our calculation and you found out that the plane strain in the x direction is this, it's dimensionless. But if we go back, we know that one of the ways you can define plane strain, it is deformation in the x direction divided by the original length in the x direction. So if I cross multiply, deformation in the x direction is equal to strain in the x direction times the original length. My strain we had was 1.4 times 10 to the minus 5th. Our original length in the x direction was how much?
12 centimeters.
12 centimeters. We're going to make that back to meters, which is 0.12 meters. So I'm going to erase this part now. Okay. So if I multiply this out, what I have for deformation in the x direction, which is 1.4 times 10 to the minus 5th times 0.12 meters, what do I get?
Uh, 1.5 times 10 to the minus 5.
1.5 times 10 to the minus 5 units,
Meters? Yeah.
meters. Did everybody hopefully get that value? Let me just check it myself here real quick. I got 0.168. Anybody else get that number?
I got 1.68 times 10 to the negative 6.
Okay.
Oh, my fault. I added times 0.12 to the whole equation.
Professor, did you write to the minus 5 or to the minus 6?
Well, that's what I'm looking now. What did you get?
I got to the minus 6.
Okay. Okay. Since you moved that decimal over, that's fine. So that would be minus 6
Yeah, it's minus 6.
meters. Okay. Because the answer I got was 0.168. So we'd move that over. Okay. So now we know the deformation in the x direction. This is plus. So what is the final length? The final length in the x direction is the original length that we had in the x direction plus or minus the deformation in the x direction. This is plus because it was in tension. So this is going to be, the original length was 0.12 meters plus 1.68 times 10 to the minus 6 meters. And if we add those together, that's the final length in the x direction. We could go back and do the same thing and calculate for y. Realize that y is deformation in the y direction divided by the original length in the y direction. And then go back and use that, the final length in the y direction. Is going to be the original length in the y direction plus or minus the deformation in the y direction. So in the end, we will come up with final dimensions in each of the three. And a sort of proof of what you've done, we know that the original volume was the length in x times the length in y times the length in z. So this is the original value. We know that the final value of volume is the final length in x times the final length in y times the final length in z. And we also know that the original volume has to equal the final volume. So if you find your values and you multiply those three together, they better come up with the same value you had when you multiplied those original values together. So we now have a method of looking at three-dimensional loading to look at safety for our system, as well as finding out final dimensions of our system. Any questions on what we did that you wanted to? We didn't do all of them, but we did one of the three. And you could do the other two just like you did that one. Question?
I just got one question.
Yes.
I think it's that I missed it, but how did you get the 0.346 for the,
For the Poisson's ratio,
for Poisson's? I missed that equation. You erased it kind of fast.
Poisson's ratio is equal to E divided by 2G minus 1. E for our aluminum 1100 was 70. 2 times the G was 26 minus 1, and we had that value. Again, this is a physical property for aluminum 1100. Any questions on what we did? Okay, I do have a quiz on this topic due on Wednesday. So let me go back and send that to you now, and I'll go with that one with you. Okay, I just sent that quiz to you. As soon as you get it, I'm going to ask you to open it up, and I'll go over that with you very quickly. Everybody got the quiz? Anybody got the quiz?
Yep.
Okay. So I've given you material aluminum 5456. I've given you its properties, the yield plane stress, the ultimate plane stress, the yield shear stress, the ultimate shear stress, modulus of elasticity, modulus of rigidity. So for 10 points, I want you to calculate Poisson's ratio. Then I'm telling you that we have a three-dimensional block of this aluminum 5456 with the following dimensions. X, Y, and Z are 3 centimeters, 4 centimeters, and 8 centimeters respectively. I've given you the forces in each of those directions, 800 newtons, 1,000 newtons, 1,400 newtons. First thing I want to know, is our block safe? And again, we're only considering plane stresses. And then I want you to set up the three equations to find the strains, sigma x, sigma y, and sigma z in each direction. I'm asking you to set up, I'm not asking you to solve it. That's worth 10 points. And then for 10 points extra credit, I want you to solve that set of three equations and give me the final dimensions of our aluminum block. Any questions on that? Okay. If there are no questions, why don't we take another 5-minute break? When we come back, I'm going to start on just a quick summary of Chapter 4 for Reactor Theory. If we have enough time, we'll start into Chapter 8, which is neutron interactions. I don't think we'll have time for that today, but I'll see you back here in 5 minutes.